infrared. That's short for IR. Okay. Infrared radiation, infrared. All right, if you remember the visible light spectrum or the electromagnetic scale spectrum, so you have gamma rays as the highest energy, and then you have X-rays, and then you have ultraviolet rays, and then you have the visible region, visible, and then you have IR, infrared, and then you have microwaves, and then you have radio waves. Okay. These are the waves of energy. Our eyeballs see in this range, in the visible range. That's what we can see. So like if I do a color here, let's say I do green, I highlight green. What's happening is the light in your room is hitting your computer screen, and the green wavelengths are reflected off of this green, and your eyeball sees green. All the other colors are being absorbed into it. So what your eyeball is seeing is actually the green wavelengths that are being reflected off of it. Okay. And then the lower energy ones are the IR infrared, which is basically heat. If you go to like a fast food place and you see the food underneath the red lamps, it's the heat lamps that are keeping the food warm. And then you have microwaves, which are made in a microwave, and radio waves, which are the waves that anything wireless works off of. So our Wi-Fi, our cell phones, our computers, internet, all that stuff uses the radio wavelengths in the air to actually transmit its information. And then above that, which are the higher energy ones, is all ultraviolet. A portion of the ultraviolet rays actually pass through, and it gets to us, but most of the ultraviolet rays are blocked out. And then X-rays and gamma rays are all in space. Our atmosphere is able to actually block those. We do, though, have ways to actually produce X-ray and gamma rays, but very, very small amounts of it, but we actually have to make it in order to be exposed. Okay, so the wavelengths of energy that we're talking about here in IR, obviously, are the infrared. When we talk about NMR, that's actually in the radio wave. All right, so very low energy waves. Okay, so infrared are these waves of energy, okay, wavelengths of energy. Basically, what the next part of this, IR and NMR, are tools that analyze our compounds. So let's say we do a reaction. Okay, let's say we have a ketone and we add sodium borohydride and we want to reduce it and form an alcohol. All right, well, how do I know I actually made it? All right, just because I take a ketone and I add sodium borohydride, it might not work or it might not go or something. Or how do I know that the reaction is done? All right, I have to have tools to analyze my compounds and tell me what compound I actually have made. So that's what IR does, and NMR does it even more so. It'll give us a lot more information. But IR tells us which functional groups are on our compound. Okay? It doesn't tell us any more than that. It just tells us what functional group we have on our compound. If we have a ketone, if we have a carboxylic acid, an aldehyde, aromatic ring, if we have an amine, if we have a ketone. So that's what IR tells us. It doesn't tell us a huge amount, but it will tell us what our functional group is. So if I am doing a reduction, if let's say I have a ketone and I'm doing a sodium borohydride reduction to form an alcohol, all right, the IR, there are signals that clearly tell me if I have a ketone, and they clearly tell me if I have an alcohol. So after an hour, I can take a small sample, put it in the IR, and if the IR tells me that I now have an alcohol, then the reaction is done. If it tells me I still have the ketone, I don't have any more, and I don't have alcohol, then that means I might have to react it longer. Okay, or it might tell me I have both. I have a mixture of both. But pretty much IR tells me what functional group I have on my molecule. Okay, and basically, here's the physics. I'm going to go through it pretty quickly. I'm not going to ask you any of these questions on the exam. I'm going to ask you more of the analysis of IRs and compounds on the IR, but I'm not really going to ask. I'm not going to ask the physics, but I think it's important that you understand it so that you understand what the signals are telling you. All right, what you have is an IR machine. Okay, that obviously it produces IR wavelengths of energy. Okay, and you have your sample right here. Here's your sample. All right. Now, organic molecules absorb infrared radiation, okay? And there's a scale. We're going to go from 4,000 wavelengths to 500 wavelengths, right? These are the wave. It's actually called a wave number. It's not really important what it means, but it's basically the wavelengths of energy that IR. So IR is not just one wavelength. It's hundreds and hundreds of wavelengths, of different wavelengths. And our scale is from 4,000 down to 500. Now, depending on the functional group, different functional groups absorb different wavelengths, all depending on the group you have. So groups that have hydrogen bonding absorb in one area of the IR. A carbonyl compound absorbs in a different area on our wavelengths. Aromatic rings absorb in another area. So all depending on the functional group, it absorbs a different wavelength of energy. Okay? And then we have a detector that all detects this. And then we have our printout. Okay? So, and our chart, so our chart is percent transmittance right here. Percent transmittance. I know this spell. I'm just kind of writing fast. But that's how much of the wavelengths are transmitting through my sample. So here's 100% of the wavelengths. Here's 0%. And here's our 4,000, and it goes down to 500. Okay? So if I don't have any sample in here, let's just say I don't have any sample. Okay? It's just an empty cylinder, or an empty tube. Obviously, all of these wavelengths are passing through. I don't have anything in here in order to absorb any of these wavelengths. So 100% of the wavelengths are being transmitted through. So on the IR, I would just have a line at 100% because every wavelength is transmitting through. Okay? Let's now say I have a sample in here, and the sample has a carbonyl and an OH group and an aromatic ring. And let's say it absorbs a few of these wavelengths. Let's say it absorbs a wavelength at 3,000 and another one at 2,000 and then another one, let's say, at 1,700. So the wavelengths at 3,000, 2,000, and 1,700, my molecule is absorbing those wavelengths. Okay, so our detector does not see any of those wavelengths passing through. It sees all the other wavelengths, okay, but it doesn't see the ones at 3,000 or at 1,700 and so forth and so on. So that IR would look like this, and then at 3,000 I would have a dip there, and then it would go back up to, and then I would have a dip at 2,000, and then go, and then I'd have a dip at 1,700. Okay, so that's basically what the IR is showing me. The IR at the very top shows me all those wavelengths are passing through. There's no functional group that's absorbing any of those wavelengths. But then as soon as I get to 3,000, those wavelengths, somewhere between 3,000 and 3,001 and 3,002 and 2,999, those wavelengths are being absorbed because whatever functional group is here, let's just say it's an alcohol functional group, all right, these bonds are absorbing this energy, okay? And at 2,000, maybe it's like, I don't know, an aromatic ring. Don't worry about these yet. I'll talk about what groups absorb where. And then let's say at 1,700, I have a carbonyl. Okay? So this tells me that on my molecule, I have an aromatic ring, a carbonyl, and an OH group. It doesn't tell me what the structure is. I might have a whole bunch of other stuff on there. I might have 3 aromatic rings. I might have 4 OH groups. I might have 27 ketones. All right, the IR does not tell me that. It just tells me what groups are on my molecule. And then you have to go and you have to piece all this, all together. So it might mean that I have an aromatic ring that has maybe an OH on one side and a ketone on the other side. So I have to piece that all together. But I might have like 2 ketones, or I might have another OH group. I don't know this. I would have to be given more information. I'd have to be given a formula or a mass of the molecule or something else. But the IR does tell me that those are the groups I have. All right, and this is basically how it's done. Whatever groups you have, those groups absorb at different wavelengths of energy. Okay, So does that basically make sense? So let me see, I have a question here from Kelly. Kelly says, so the dips determine the functional group. Yes, that's exactly right. Well, yeah, what the dip is implying is that those wavelengths are being absorbed by a different functional group on my molecule. If I don't get an absorption, if it just transmits through, then there isn't anything there that's absorbing that energy. All right? All right. Okay, so this is a sample IR. And what I'm basically going to do is I'm going to use this as the notes and kind of write on here what you would see, where you would see it, what groups show up around where. Okay. Now these numbers are not exact, so I don't want you to, these are approximate locations. So the first group I'm going to talk about is an NH, are molecules that have nitrogen and hydrogens on them. So obviously amines, either a primary amine, either an NH or an NH2. Okay. And they show up roughly around 3,300 to 3,500. So roughly between here and here. And this is rough estimate. I mean, it could be at 3,200. It could be at 3,600. It could be at 3,400. It doesn't matter, but it's roughly in this location. And what you'll see is usually very sharp peaks. Because what we'll also see is ones that have very broad peaks. A broad peak is where it's more rounded. It's like something like that. But if you see a very sharp peak around this location, it roughly implies, it can imply, I'll tell you some things that it could also mean, but it usually, I mean, if you have a nitrogen on your molecule, if you know that you have a nitrogen on your molecule and you see this peak roughly in this area, then that would imply that you have an NH. Okay. If you get two peaks, sometimes it can mean you have two hydrogens there. So if you have like this and have two peaks in this location, that might mean that you have an NH2. Not always. You could an NH2 can also mean one peak. However, if you do see two peaks, most of the time, maybe 80% of the time, will imply that you have two hydrogens on your nitrogen. Okay. If you only have one hydrogen, then you'll see one peak. If you have no hydrogens, then you won't see any of these peaks. There is no peak for just a nitrogen and a carbon. It's just nitrogens and hydrogens. Okay? And what I like to do is I like to go back and forth. Let me go to the, let's go here. Let's go to, I want to go to Google. And I just kind of want to show you some examples of IRs that have these in them. IR amines. Just so that we can start getting used to seeing what these look like. Okay, so here's a perfect example. Here's one right here. You can kind of see that peak right there at 3288. You see that peak stretch right down. That implies an NH. If you look at the formula, here's an NH. So there's the peak right there. Notice that there's only one hydrogen on there. All right, this one has two hydrogens on it. All right, see that has two peaks. It doesn't tell me what the sample is, but you can, again, roughly see it's about 32-ish around there. Let's see if we can find an NH2, and we can see the two peaks. There you go. Here's kind of an older one. Okay, you can see these two peaks right there, implying you have an NH2. So there's your NH2. Let's not worry about any of the other peaks yet. I'll talk about these. Okay, so again, I like to do this just to kind of show you what these actually look like, so you can start getting used to them. Sometimes they're bigger, sometimes they're not so obvious. That's the hard part about IR. The thing is water actually shows up in this general location, and water is pretty much in everything. So sometimes you'll see a peak, like here's an example of one, which I don't think this is actually an amine. That is probably water. That's kind of how water looks. It usually has this other little hump to it. It's a little more broad, too. It's not like a sharp peaks. So sometimes there are peaks in this location, and people think they're amines, but they might be water. So if you're kind of squinting and be like, I'm not too sure, most likely it's not, but you would have to be given other information. Okay, IR is not the end-all, be-all. NMR really tells us a lot more information. But with the combination of IR and NMR, you get a complete story. Okay? So just be on the lookout for stuff like that. I'm going to give you examples on the exam that are very obvious. I'm not going to give you ones that are hard to see. Okay? Okay, so that's an example of an amine. All right, the next group that absorbs roughly in the same location, I'm going to do it in a different color on top of it, are alcohols. Okay, they are OH peaks. These roughly show up in the same location, but they're very broad, and it's very characteristic of alcohols. The numbers they give you in your book are about 34 to 3600. 3400 to 3600. Again, that's roughly about the location, and the way it will look is it will look more of a broad peak like that. Okay? So you get more of this broadish peak. But it's very characteristic. It's like you can immediately look at an IR and know that you have an alcohol. There is no squinting or anything like that. So there are times where you're looking at, if you see peaks, you see how broad these peaks are? All right, you see that? That's just a broad peak. It means they're also pretty large too. It's kind of obvious. It's not like you have to squint about alcohols. Here's another example. Here's another one. I mean, all these are classic, very characteristic examples of alcohols. Very broad. Okay. Let's see. Andrea said, "Would carboxylic acid?" I'm going to talk about a carboxylic acid. You just wait. We're going to go over through all the functional groups. Each one has their own characteristic peak to it. Okay. All right. Next one I want to talk about is aliphatic and aromatic. So aromatics, I'll put them here because this chart's going to start getting a little crazy. Aromatic versus aliphatic. All right. We've talked a lot about that. Remember, aromatic is a benzene ring. Aliphatic is not a benzene ring. So anything that is not a benzene ring. It could be a cyclohexane, all right? It could just be a straight chain. It's anything that's not an aromatic ring. All right? The aromatics show up just to the left of 3000. I mean, we are talking just to the left. And aliphatics are just to the right of 3000. So if you look at 3000, you can pretty much draw a line. Obviously, my line's not going to be completely straight. You can draw a line, and things just to the right are the aliphatics, and things just to the right, the left, are aromatics. And literally, it's right at that 3000 line. These are very sharp, so you'll kind of see like a whole bunch of peaks here. It'll be very sharp, and the same thing for an aromatic. Very sharp peaks. All right, so let's look at those. Actually, you can just look at anything here. Now, you will always have peaks there because your molecule always has like carbons and hydrogens on it. So if you look at here, I have aliphatics. I do not have an aromatic ring. Here's 3000. It's hard to see. And look at this. This basically lines right up at 3000. And those peaks just to the right of it are all of the aliphatic hydrogens. Okay? Here's one too, aliphatics. All right. Now, if you have aromatic and aliphatic, they will actually show up all on top of it. Okay. So let's actually just look. Okay, here's an aromatic and an aliphatic. Okay, so you see 3000. If you draw that line directly up, okay, see you have peaks to the right, which are the aliphatics, and you have peaks to the left, which are the aromatics. So you kind of see both. And literally, you can cut it right in the middle. All right, here's also aliphatic. This is an ester, but it doesn't matter what the group is. You draw that right up. It goes right to it. Let's see if is this just aromatic? This is both. I want to see just an aromatic one. Let's just do IR aromatic. These all have aliphatics. It's not really a good one. Can't really find me. Oh, perfect. So here is aniline, which is amine and benzene, so it's just the two. So here's 3,000. If you draw this 3,000 up, you can see it's just to the right of those peaks. And then you even have the two amine peaks right here. All right, this is called a shoulder band. We're not going to see that, talk about that at all. Okay, so that kind of had both in there. Okay. All right, now I want to talk about a carboxylic acid. And this might answer a few of those questions that I see up there. Carboxylic acids are gigantic peaks, all right? And what happens with a carboxylic acid, so it's basically looking at these right here, this OH on a carboxylic acid. These are very, very broad. This is also so characteristic. It's so big and so broad. This is basically how it looks. What happens is, here, I'll just kind of show you where the range, there really isn't a range. They say from 2,500 to 3,100. From 25, so here's 25 to about 31. I'd say it's bigger than that. Basically, it looks something like this. It just kind of swoops this whole entire area. And pretty much any other peaks you have here are buried underneath this. So you can't have peaks on top of other peaks. You either have to know that they're there, or you just won't see them. It's a possibility that you won't see them. What does happen, okay, is these aliphatic peaks. Aliphatic peaks are usually very big, meaning that they go down very, very large. So what you'll actually see in a carboxylic acid peak, I'll draw it up here, a smaller view, is it'll come down, and then you'll kind of see these little peaks right here, and then it'll go back up. Okay? So what that basically is this big rounded peak is the carboxylic acid, and these things that are poking out are the aliphatic aliphatic hydrogens and carbons that are poking out here. So you'll kind of see them right there. Okay, so I'll show you what that looks like. But that's basically aromatic again. I'm sorry, a carboxylic acid, very characteristic. You would never get them confused between that and an alcohol. All right, and I'll show you the difference. All right, so here's kind of a good example. See how broad this thing is? It starts here and it ends over here. Okay, it's not like these are like going down and going up. It's sharp down and sharp up, sharp down, sharp down, sharp down. These start here and then it just keeps going, and then you can kind of see these little things out here. You know, that's implying that you have other things underneath it. But pretty much carboxylic acids swamp everything out. Here's a better example of that. You can see that the carboxylic acid is here, and then these peaks right here are our CH peaks. So you can kind of see them. So our carboxylic acid is overlapping our aliphatic peaks. Okay. So again, here's an alcohol. Notice an alcohol goes up, goes down, and it comes back up. Then it goes down for aliphatics. Carboxylic acid just swamps this whole entire area. It just keeps going and going. All right, here's a carboxylic acid. You can see the aliphatics hanging out there. Here's another. That's an alcohol. That's an alcohol because it's coming up. That one might be hard to tell. That's not a classic example, but it's pretty good. But here's a carboxylic acid. So it should be pretty obvious. There isn't anything tricky about this. I don't want you to think like it's going to be hard or tricky. Like, that's an alcohol. All right, comes down, goes up, and then you have your aliphatics. Carboxylic acid just completely swamps it all. But also in a carboxylic acid, you also have a carbonyl in a carboxylic acid. So you will also see a carbonyl peak, which we will talk about. All right, so carbonyl peaks do show up in carboxylic acids. All right, so I hope this kind of gives you an idea. So here's one. That's a carboxylic acid. Again, the same type of thing. You can look at this and just know you have a carboxylic acid, you have an alcohol. Very, very obvious. Okay. If I had an alcohol and a carboxylic acid, I would not see that alcohol. That alcohol would be so buried underneath that carboxylic acid. Everything is buried under a carboxylic acid. If you had an amine, I think that Kaylin asked, so what happens if you have an amine? basically, and an alcohol, I don't think you would even see the amine peaks. They'd be buried underneath that alcohol peak. But again, every sample is different. So there is no absolute answer for any of those questions because it just all depends on your sample. It depends on where things show up. All right? Okay, so any questions up until now on these groups that we've talked about? Which one's next? Let's talk about blue. All right, next group I want to talk about is an aldehyde. Aldehydes are very characteristic, and specifically we're talking about the hydrogen on an aldehyde. We're talking about this hydrogen right here. All right, that hydrogen is very characteristic. It shows up just to the right of the aliphatics. Right of aliphatics. In fact, sometimes it's attached right directly on the aliphatics. Let's see if they give a number here. I don't know if your book actually does this. This is something I kind of do. Let me see if the book has a number. I don't think so. Yeah, almost. Okay. But what you're looking for are the fangs. You're looking for fangs. What happens is you get these two sharp peaks, roughly the same size, just to the right of the aliphatic. So the way that it would look, I got my carboxylic acid there, but I'm going to do it in blue. So you'll have your aliphatics, and then you'll get these two of the same size fangs right there. Okay? Let me see if I can find numbers for you. I think the numbers are right in here. I think it's like 20. Let's see. And also, it's a very characteristic peaks. Sometimes you can see both fangs. Sometimes you can see one of them. So here, they kind of give you numbers. About 27.5 to 28.5. Again, the numbers do not rely on these numbers hugely. 27.5, 28.5. But it's the area that you're looking for. If you see fangs like down here at 750, that's not an aldehyde. All right, that's not even close to the area. It's the general area. It might be at 2700 and 2800 on another molecule. It might be 27.5 and 27.8. I mean, who knows? But it's roughly in that range. Okay? And they're just to the left. So here's a great example. So here are my aliphatics. And you can see just to the right of it, there's these two same size peaks. And they look like fangs, and they're sticking out right there, 27, 25, 28, 27. All right? On this one, I obviously don't have any aliphatics, but I have the fangs. All right? Now, other times, they're actually hard to see because that first fang, here's a good example. It gets buried inside of the aliphatic. So you can kind of see that little bit of a fang right there. Again, if you're squinting, you could say, yeah, it looks like I have an aldehyde. But again, you're going to look for a carbonyl peak. But you have to be given more information in something like this. Like, is it really an aldehyde? The fact that I have this peak here at B at the 27.5, probably characteristic I have an aldehyde. I'm pretty certain, probably 95% certain I have an aldehyde there. Otherwise, I would not have that peak there. Okay, like here, there I don't see really any fangs. So that I would be like, I highly doubt I have an aldehyde, or here too. Most likely I do not have an aldehyde here because I really don't have any fangs showing up. All right, it's very characteristic. So there I got fangs. That one I've got fangs. Again, they don't have to be exactly the same size, but pretty close to it. There I've got fangs. And again, you're looking for a carbonyl peak, which I'll just let you know, they show up roughly around 1750, which is kind of a big one. So there are fangs, here are fangs. Fangs everywhere. Okay? So that's how you can tell an aldehyde. Let's get to triple bonds. There are only two more functional groups I want to talk about. Triple bonds show up roughly in this range right here, either a CC triple bond or a CN triple bond. Nitrile. They show up about 22.1 to 22.6, so 22.10 to 22.60. Again, and it's usually a sharp peak. Okay, you'll see a nitrile in that region. Okay. The other thing is if you have a terminal triple bond. So this is a terminal triple bond. Okay, so a terminal triple bond, remember, has a hydrogen at the end. If you have a terminal triple bond, not only will you see the triple bond at this area, but you'll see this hydrogen, which this can get confusing, roughly in the amine region. All right, so you'll see that hydrogen somewhere around the 3,000, about the 3,200 region. Okay, so this is why it's important to actually know where everything shows up. Why you have to be given more information, because you might say, oh, I have an amine, but in reality you have a terminal triple bond. So right here is a perfect example. So you have a peak at the 21,2, but then you have this peak at 3,300. And you might be thinking, that's an amine. Well, oh, wait a minute, I have a triple bond peak. Well, that's not an amine anymore. It's the hydrogen off of a triple bond. Okay, so these are things that you have to piece all together. Okay, now if you just had a nitrile, or if you just had a triple bond that's not terminal, it would not show a peak there. So here's a nitrile, it just shows a triple bond there. It does not show anything in this region over here. Okay, does that make sense? I don't know what I'm looking at down here. Okay, so like that's a terminal triple bond. So if we analyze this, we have the triple bond, we have a terminal triple bond because we have the peak here, and then notice we have, I'm sorry, that's triple bond right there. That's my aromatic. I'm sorry, my nitrile. I don't have a triple bond here. Here's my nitrile. I couldn't see that. That was hard to see. And then just to the left of 3,000. Okay? Okay. And then lastly, we have our carbonyl peaks, which show up around 1,700 to 17.5. Let me look exactly. Yeah, it looks at 1670. I'd say more like at 1,700. So roughly around here, 1,700 to about this range right here at 17.5. And these are big, sharp peaks. These are carbonyls. So ketones, aldehydes, carboxylic acids, esters, anhydrides, anything will show up in that region over there. Okay? So I think that should go a little bit over here is our triple bonds. Okay, anything lower than this is called the fingerprint region, and we are not going to analyze this. I don't even know how to analyze it. All right, people don't really learn how to do this anymore because NMR will give you more information. So anything in here, we are basically going to ignore. Okay. Now your book has a really great picture. Let me just talk about this real quick, and then we'll call it a day. Let me open up the book real quick and just show you this page, which kind of is a summary of everything that I just talked about. What I usually do is I give this to everybody on the exam, but since you guys will have this available to you, let me see where it is. Hold on one second. I don't want to share the screen because I think it's in one of the exams. I'll show you the exams. Let's see, final. All right, it's right here. I'm sorry, guys. You guys are asking questions. What range? What range are carbonyls again? Around like the 1700. Oh, Anna. Okay, never mind. You guys got it. Good. All right. Let me show you this slide. I'll post it. But this is kind of in your book. It's page 440. It's on page 440. 440. And this is kind of a summary of everything that kind of shows where everything is. So in this range, that 2,700 to 3,500, you have NHs, OHs, and then you have the aromatics and the aliphatics. You also have the aldehydes. So if you want to add to this, or if you want to print it out, this can kind of organize it a little bit better. Your triple bonds are in this 2,200 range, which remember, terminal hydrogen will also show up in the NH. And then really the only thing I care about here are the carbonyls. And our carbonyls kind of show up in that range over there. Okay? So that's basically IR. I actually honestly have taught you everything that I know about IR. That's kind of everything. So what we will do on Thursday is we will go over problems. That's the best way that you learn how to do this, is by doing problems. And we're going to do lots of problems on Thursday. So don't miss Thursday. I would suggest that you guys come on Thursday.